Smartphones for deaf people, turning signs into sounds. The purpose of this presentation is to discuss the topic of deaf-hearing communication. That's when deaf people communicate with hearing people. This requires translation between two languages. This problem has two values. One is a scholarly value. Research in gesture recognition has a number of applications besides translation, such as robotics, controlling robots. But the most important value, at least for the purposes of this presentation, is the social value. Deaf people often feel isolated, even from their own families, and this tool may well lead to new levels of integration of deaf into society. Now, this presentation, I was advised to tell them what you're going to tell them, then tell them what you told them. So this is where I'm going to tell you what I'm going to tell you, which is basically this. We're going to talk about past solutions, present challenges, and future possibilities. Past, present, and future. Let's start off with past solutions. In the relatively distant past, deaf people were trained to act like hearing people. There were deaf schools set up where deaf children were not allowed to use sign language, and they are punished if they use it pretty severely in some cases. Strangely enough, Alexander Graham Bell, the inventor of the telephone, his mother was deaf, as was his wife, and he spent much of his life trying to find solutions, technical ones and training ones for the deaf community. For many years, physical solutions have been attempted. There have been some, basically false type things like ear oil, which was just a sham, but also tools like a little ear Victrola, and more modernly, still to this day, cochlear implants are surgically implanted and connected to the hearing centers of the brain, and so there have been technical solutions in that way, just to change the physical body. Not all deafness is curable, if you want to call it that, through cochlear implants, and there's a controversy about that in the deaf world. Anyway, the thing has been attempted. So, moving on, other solutions have been technical, from pencil and paper, which is fine if you're sitting in a room, but it may not be good at a drive-through window, and it slows down communication compared to natural speech, whether it's people talking audibly or using sign language. The machine to the left there connects up to an old-fashioned telephone, and it works well. It's called a TTY. The only problem is you need to have one on both sides of the transmission, otherwise you can't talk to them over the phone. And again, it's still typing. Texting has become very popular. As a matter of fact, it's revolutionized the deaf world, because now the deaf can communicate remotely using text messages. Again, though, it's still text-based and it's very limited. Video calling is also a solution, but that just enables two signers to communicate. It doesn't allow communication between deaf and hearing people. Sign language is a fact of life. No past solutions have eliminated sign language. Today, sign language is legally mandated by the Americans with Disabilities Act. The government has to provide sign language translation for almost all government services, and there's requirements for companies as well, just like wheelchair access. What that means is that these companies have been created that provide relay services, communications, and interpretation for deaf people. Since deaf people can't communicate directly with hearing people, not even their own families in many cases, what happens is a deaf person calls from basically uses his remote control on a TV and activates another TV at an interpreter site, and then the hearing person can listen to the interpreter talk, and obviously the communication is done through this, what's called a Sorensen VRS. Sorensen's a big company that does this. VRS is a video relay service. That's what the state of the art is right now. It is very imperfect. Example, my friend Wesley. One Saturday night he fell on his bicycle, hit his head, and the entire right-hand side of his face was swollen up. His right eye was closed shut. This is a picture of him the day after, when the pus had somewhat subsided. At the hospital, there was no interpreter, and the nurse told me that we treat him as if they're unconscious. The relay service was not, I don't know why they didn't have that available in the emergency room, but it wasn't there. I mean, because I guess there's not enough deaf patients. So he got what treatment he could. But anyway, if he had had a device that was mobile that could have done some small interpretation, it would have certainly helped him at the hospital. So let's turn now to present challenges. Present challenges are basically adding and augmenting voice recognition technology, which already exists. It's a proven technology, and adding to that a developing technology, gesture recognition. ASL to text. ASL stands for American Sign Language, and I want to be able to convert that into text. And then, of course, we can take the text and convert that into audible English. That's already done on almost every computer you buy these days. That's the goal. In order to accomplish this goal, we need 6 pieces, most of which have already been accomplished. Text to voice, most people have seen that, where you can just type in text and print that out. Also, even translated from one language to another. Google Translate does that. Voice to text, that happens. Talk to Me is an example of a mobile app that does that, and so we can basically move from text and voice and even different languages using existing technologies. Text to sign language is also possible. There are dictionaries you can go to, like ASL Pro is one of them, and you type in a text string and it will give you the sign for that. The problem is there's a linguistic issue here with these changing the American Sign Language text into English text and the English text into American Sign Language text. The words are similar, but the language really is different, and the order is different, and there's all kinds of differences. It has been shown to be its own separate language, and I can tell you from personal experience, it is. That requires probably a linguist along with a professional interpreter to determine how to do that. But the big technical piece remaining is gestures to text. That's what I want to work on. Now, there's a couple people that have been working on this. This fellow here is Christian Vogler at Gallaudet University. He's one of the leading people in this field, and he works for the largest deaf university in the world. This text here is an example of how the order of the words is different. Now, of course, not all sign language is words at all. Some of it's just showing what's going on, so there's no way to translate into words at all. But basically, there's many different ways of doing this translation, and none of it's perfect, and it's computationally intensive. It takes a lot of computer horsepower. Some people, that's if you use computer vision. This is computer vision, cameras. If you use gloves, which is the more reliable but less, I don't know what you want to say, attractive to the end user, gloves have been used to be able to find positions of the hands and to measure these gestures with more accuracy. But nobody that I know of wants to use gloves. Everybody wants to use cameras. I mean, both the researchers and the people who would use the tool don't have an interest in gloves. Even with the gloves, there's not that much accuracy involved in the sign language translation. But the good news is it's not computationally intensive to use the what's called a nearest neighbor method to compare these basically feature vectors between the test and training cases of a set, say, of hand images. There's a guy from MIT named Robert Wang who used a Hausdorff-like image distance. This is the equation for it, for a nearest neighbor method, and it worked, but didn't work on very diverse vocabularies. Basically, if the hand sign was not distinctive, very distinctive, it was unable to detect the difference. For example, this is the letter E, M, N, S, and T. You can see that they are different, but they're similar enough that a camera-based method, even a nearest neighbor, feature vector method, may not be able to detect them. In the case of Wang, it was not able to do that. So that's a continuing problem there. But just in the last couple of years, there have been several, I mean, maybe a dozen papers on fingerspelling using camera, imaging methods, image processing methods. None of the results have been particularly significant, although it is clear that the experts tend to favor cameras over gloves. I am introducing a one-handed solution for a very specific purpose. One hand performs fingerspelling, and the other hand holds a iPhone or an Android or whatever it is. And my contribution here is to attempt to process the image and use it for this text, or sorry, image to text, ASL to text purposes. Ideally, would be the phone would audibly say, hello or whatever it is you signed in there. Last semester I attempted something called it was called canny edge dilation. I started off using a thresholding technique similar to one of the papers that was listed above, and I was able to extract the hand image. And then what I did is I tried a bunch of different ways of comparing the test set with the training set, and what ended up happening was this canny edge dilation method was the best one that I tried, although I didn't get a chance to try as many as I would like. This is what the training set looked like. Hit or miss was one of the techniques I used. Barkaki was the benchmark technique that I started off with. These are the signs that tend to have difficult, it's difficult to determine one from the other because of the mathematical techniques involved. This is the test set, so I use a different background. Basically, it's the same. It's my hand, so it's the same hand. And here I went into MATLAB and I thresholded the image, stripped off the unnecessary stuff below the wrist, and I was able to. I tried skeletonizing it. I tried finding the key feature points. I tried a lot of different stuff. This is in the training set, and this is on the test set here. Same thing. You can see these images don't look anything like each other, even though the hand looks pretty darn similar. So I don't know what to do there. What I found was that the canny edge detection solution worked the best, and when I dilated the canny edge and then subtracted errors from that edge, basically, well, I'll explain that in a minute, I was able to get the best results that I had. The experimental results I had were that I tried 7 different methods in this particular canny edge dilation. It was the best solution. Now I will say this: I took basically set A and set B, and I subtracted set B from set A, and that would be the regular results, 12%. But when I subtracted the errors, in other words, those things that were not in set A that should have been, then I got 35%. So that's why the difference was there. I tried that in a couple different techniques, and it always improved the results. Disadvantages of this method: dependent on lighting conditions, fails if they have flesh tone backgrounds. The thresholding thing determines what the flesh tone is, and if there's flesh tones in the background, then it won't be able to detect the hand. It requires calibration to a specific user. Of course, different hands are different shaped. It has limited applications: text messaging, sign activation, which I would imagine would be similar to voice activation, and some of the numbers in ASL are the same as the letters, so it can be. We need to figure something out on that in the future. Most importantly, the alphabet's only a tiny portion of translation, so complete translation may be many, many years away. Some criticisms. One of them that I got when I submitted my paper was that ASL is not a real language. I don't know how this person knew that, but it's not the case. It's a misunderstanding. ASL is a real language. Mobile translation not technically feasible. Well, that's why we're studying it. Some people say it's not going to ever be feasible. Well, our job is to figure out a way to make it feasible. And other people say it's just too expensive. It's cost prohibitive. But when you look at the costs of not doing it, it appears to be more worthwhile. So the real value, though, of course, is the social value that comes. So future possibilities. I got to do a better job of flesh tone thresholding and definitely some other algorithms and techniques. There's so many things to try that I haven't tried. Some other applications might be military. You know, if there's cases where you need to be silent, you can't talk or use audible communication. If a robot could be, even a combat robot could be commanded by hand signals, that might be helpful. This technology might be able to do that. At some point, one of these smartphones could be a universal translator, translating sign language to audible English, sign language to French, you know, sign language to other American Sign Language to French Sign Language, and sign language to text. Basically, a deaf person could look up a word in the dictionary, which today he cannot do. At least not using signs. Blue sky, who knows, one day we might have a deaf leader of the world and he could communicate in a conference call using this technology. So who knows what what's in store. But basically, the past solutions have tended to isolate deaf people. Present research, promising, we can debate the question on that, but the future potential is definitely for broad applications and big impact on people's lives. So the question I'll leave you with is this. Is gesture recognition a technology whose time has come? Thank you for your attention.